about membrane osmometry. So we left off last time making this assumption that we're working with very dilute solutions. Pretty reasonable. We can define these definitions here, where the volume, total volume of our solution, i.e. total volume of solution is approximately the total volume of our solvent. So N1, V1, and we said that V1 is approximately V1 is approximately equal to our molar volume. And with that, we were able to make some basically simplifications and substituting in these approximations into our equation above here, and we got this expression. So this is a really, really nice equation because look what happens when we have chi equal to 1/2. So we said last time that if chi is equal to 1/2, we basically have zero excess chemical potential when we're at our theta solvent. And you see when chi equals 1/2, this expression disappears, and we're left with this expression right here. Hopefully this looks familiar. EV equals nRT. The ideal gas law, again, the material is behaving ideally, and that's what we get. So there's one more simplification that we can make. So if we instead define variables in terms of our concentration of polymer, C2, instead of the volume fraction, and we know that the concentration of our polymer is just going to be the total mass of our polymer divided by the total volume. So substituting this in and dividing our osmotic pressure by our concentration gives us this expression right here. So now, again, we get kind of the thing that we were looking for initially. How does the osmotic pressure and how it relates to our osmotic pressure as a function of Mn and as a function of chi. So this is kind of the power of this osmotic pressure. We can now relate our osmotic pressure that we can measure, because we know we can measure that with an osmometer, to our average molecular weight and our chi parameter. So we can also say, actually get rid of this. We can also see that this has a form of a virial expansion. So let's actually look at this equation right here. So a virial expansion is pressure as a function of several variables. Specifically here, we see that it's a function of concentration, or basically as a function of C here. So we can see and match our terms with our virial expansion. The virial expansion is a very general equation. It expresses the pressure of a many particle system in equilibrium as this kind of power series as the number density or as a function of your concentration. So it's a pretty thing. If you've taken several chemistry courses, again, you'll see this kind of expression, that virial expansion. Not chemistry courses, excuse me, but thermodynamic courses. Specifically, if you've taken any statistical mechanics courses, so you'll see this expression appear over and over and over, and specifically these virial coefficients. So virial expansion, pressure as a function of these kind of concentrations here. And each of these virial coefficients, A sub 1, A sub 2, A sub 3, that's kind of what we're going to kind of quantify here. So we see that our first virial coefficient in our expression above here, so let's go back. Pressure here, you multiply by the concentration here, concentration squared. So this is our A sub 1. And this would be here, oops, excuse me. This whole thing here would be our A sub 2. So in terms of our virial expansion, our virial equation, we get our first virial coefficient and second virial coefficient. So how do we use this information, use this equation to basically measure properties like M sub n and chi? Well, we're going to create a similar plot like we did for our intrinsic viscosity measurements. So we are going to use this and plot the reduced osmotic pressure, or our osmotic pressure divided by C2 as a function of C2. So when we do that, we get, again, let's look back at this expression. So pi over C2 as a function of C2 is going to give us, is equal to RT times, let's go back to this expression right here, RT times 1 over M N, excuse me, E times, excuse me, over N, and then plus our function here. Let's go back one more, just rewriting this. So plus 1/2 plus minus chi P1 x2 squared divided by mn squared. So just what we see here times our concentration, C2. So just all we're doing is working off of this expression right here. So again, if I plot my osmotic pressure divided by concentration as a function of concentration here, this is just a linear equation. So we see osmotic pressure increases as concentration increases, and we can extract some critical information. So our y-intercept is just going to be this. Our slope is going to be this. And this is going to be kind of the powerful expression that we have to kind of analyze the data here. So y-intercept, slope. So again, we could measure our molecular mass, number average molecular mass. Here, we could also get this information, but the key kind of parameter here for the slope is this expression right here. So let's look at some different scenarios. So if I add that 1/2 minus chi. So if chi is ideal, so if it's a theta solvent, equal to half, what is the slope? It's going to be 0. So that's my slope value. What if my chi is in a good solvent, i.e. less than a half? Well, if chi is less than a half, it is going to be a positive slope. If my chi is greater than a half, chi is greater than half, remember, chi 1, 2 essentially tells you proportional to the energy 1, 2. So if chi is high, E12 is high, they don't like each other, so that is a bad solvent here. So this is good solvent, this is bad solvent, and this is kind of the power of the expression here, and my slope is going to be negative, just as you kind of see right here. So from a single series, appreciate kind of the power here. From a single series of measurements, we can get both parameters. We can get m sub n, and we can get chi. So I'll get rid of hint for an exam. So anyways, so what are the key assumptions that we made in our membrane osmometry derivation? Well, there's two key assumptions. One, we assume a mean field conditions. We've talked about mean field before, specifically in the context of Flory-Huggins theory as well. We also assume a dilute solution. So that was kind of the key assumption that we made to simplify this expression. So mean field, these are kind of contradictory, basically, these are really actually, not somewhat, they're very contradictory kind of assumptions. It's because mean field conditions break down in dilute solutions. So we have to have our experimental conditions meet the following conditions. So we need to be mathematically dilute, i.e. our volume fraction must be much less than 1, but our system must be thermodynamically concentrated. And what we mean by that is that our concentration of our polymer must be greater than the overlap concentration. So this C2 prime, we've kind of mentioned it briefly before in a previous video, but our experimental conditions must be very specific and are only valid in the semi-dilute conditions. So this parameter, this C2, is our overlap concentration. It's where our polymer coils just begin to kind of overlap in our solution, hence the name. And around this concentration, you can see here in our little schematic, the polymer coils are slightly interpenetrating, so that our mean field assumptions are basically, or the mean field assumption of equivalent local environment is accurate. So if you want to kind of look at this, just at this concentration, our polymers are just starting to kind of overlap. So on average, if we just did the mean field theory, we're, basically they're starting to kind of interpenetrate. So their coils are kind of starting to mix. The spaghetti strings are starting to entangle, almost entangle, or not entangle, but start to kind of feel each other and overlap. So we're going to be at a concentration that's greater than C2 than this overlap concentration. So again, our mean field theory is accurate because it's just this mess of polymer coils kind of overlapping. So this allows us to apply kind of our Flory-Huggins theory, applies our mean field theory, and that it's accurate. So, but there's still enough solvent right at the overlap concentration that the assumption of a dilute solution is accurate. So we can still make the assumptions. Again, we have to hit those two. So C2 must be greater than C2 star, but phi 2 must still be equal to 1. So not easy to hit these experimental conditions, but we have to be there in order for this theory to work. So that overlap concentration is simply the mass of a polymer molecule. So the mass polymer divided out, we dealt with this before, divided by the volume of that polymer coil. So we know that m is proportional to n, so to the first power here. So let's look at how C2 scales with n. So the top here, we know this is n, we know this is n to the 3 halves. If you just assume again this ideal solution, you can see here that our concentration, our overlap concentration, scales as n to the minus 1 half. So this is a very interesting scaling law because it says that at large values of n, our overlap concentration is really small. But that should make sense, right? If my polymer is really large, the concentration at which these polymers will overlap one another should be, very small concentrations because my polymer is huge. If my n is very small, then basically this is saying that C2 is going to explode, right? Because if my polymer is small, I need a lot of polymers in order to hit this kind of overlap concentration here. So this implies the conditions which our derivation can be achievable under a broad range of experimental conditions. So that's kind of the key things here. So the overlap concentration gets quite small. So we can hit this experimental conditions. We could basically be in the kind of correct regime where our theory holds true. So that's kind of this idea of overlap concentration. So again, basically the idea is that the polymers are just starting to overlap and slightly interpenetrating. We're going to kind of get back to this idea of interpenetration and entanglements a little bit later on in the course in the exam 2 material. So, but for now, those are kind of the key assumptions in this derivation. So that's membrane osmometry at a nutshell. So remember, back to basics. So we placed dilute polymer solution container, basically adjacent and adjoining, basically only separated by a semi-permeable membrane. Excuse me, a semi-permeable membrane that's filled with only solvent. So the semi-permeable membrane only allows the passage of the solvent, not the polymer. So that free energy gain, that thermodynamic driving force called osmotic pressure, that's due to the free energy gain in the entropy of mixing, allows the solvent or pushes the solvent to move in the direction of the polymer solution. Mixing, increasing your entropy, increasing this kind of competing osmotic pressure and your kind of gravity force as well. When the flow stops, we're at equilibrium. So once we're at equilibrium, we can measure osmotic pressure experimentally, and we have this expression here, this critical expression that we will deal with that allows us to, in a one series of measurements of osmotic pressure normalized by concentration as a function of concentration, we can get the y-intercept, which is our number average molecular weight, and our chi parameter as well. So this is kind of the critical thing that we're going to be dealing with in this. Excuse me. This is kind of the key aspect. Again, experimentally, from one series of measurements, we can get this, and we could get chi, all in one shot. So really cool, really powerful measurement. And yeah, that's about it for membrane osmometry. Questions? Thanks. Have a good one. Good night. Bye.